process. Okay, so another way to transfer heat is via radiative heat transfer. So radiative heat transfer is happening all the time. So it turns out that every material is constantly emitting photons, so light. And physically that happens basically because atoms in a material, oh, I lost my picture. Because, atoms in a material are always jiggling around. And as they jiggle around, let's say, you can imagine a material like salt, for example, sodium and chloride. If those things are jiggling around, that means you potentially have, fluctuations in charges, like a positive charge and a negative charge kind of fluctuating around near each other. And that'll sort of randomly emit electromagnetic waves, so photons. So it turns out all of this stuff is really rooted in quantum mechanics, and it turns out that the amount of the energy released by photons has a lot to do with the temperature that you're at. More jiggling equals more emission. So higher temperatures equals more emission. But there's something even more interesting than that, which is that which photons does it emit also depends on temperature. So this was described by Planck. I'll get my history wrong, so I won't tell you the year. But essentially, very hot things emit shorter wavelength light. And so the one that you're the most familiar with is the sun. So the sun is so hot, it's close to 5,000 degrees C. Degrees K, that it essentially emits visible light. Well, at atmospheric conditions, so at 300 Kelvin, that's also still happening. It just turns out that the wavelengths that you're emitting at aren't the same. If it turns out that at 300 Kelvin, the peak emission happens somewhere around a 10,000 nanometer wavelength, which corresponds to pretty deep infrared. So you can't see it, not with your naked eye. An infrared camera can see it, but anyway, we're emitting photons all the time and emitting energy, and that is emitting energy means that energy is being carried away from something, and that means that heat transfer is happening. Planck showed at the onset of quantum mechanics that you can actually describe the maximum amount of heat that is carryable according to the laws of quantum mechanics turns out to go as some fundamental constant called the Stefan-Boltzmann constant times a factor of temperature to the fourth power. This is a really famous relationship, Planck's law. So that constant of the universe is a well-known number. It's called the Stefan-Boltzmann constant, and it's pretty easy to remember. 5678. It's 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth, whatever units it takes to make it SI. That turns out to be the theoretical upper limit to how much heat can be transferred, meaning that if you look at that process of emitting energy by photons is much more efficient when the temperature is high than when it's low. So we'll come back to that in a second. All right, so real materials, it turns out, don't quite reach this upper limit from quantum mechanics. They're usually a little bit lower, and how much lower depends on what the material is. So what we typically do is assign a fudge factor. It's not a fudge factor called the emissivity. So rather than using Planck's law directly, we'll just insert a factor called the emissivity that describes how much energy is being emitted from a real surface. And so for metals, that number is usually abnormally low. So for a pure metal, that number might be around 0.1. But for most other materials like ceramics and fluids and most things, especially rough things, tend to have emissivities pretty close to 1. So emissivity is always a number between 0 and 1, by the way. Because 1 would be the upper limit. But typical values tend to fall in between half and 1 for most materials. All right, so now really I wasn't looking to figure out how much was emitted. I'm looking to figure out the net exchange. This is heat transfer. So the transfer goes both out and in. So usually, depending on the context of the problem, usually there's some other surface that's emitting stuff back at the surface you're trying to transfer heat from. So that may be the atmosphere. So the atmosphere is all around us, and out in space it's close to 0 Kelvin, or it might be a physical something physical that's in close proximity. So if I take the difference between how much heat is going out from a hot surface and how much is coming in from a cold surface, I can use that modified version of Planck's law to get an expression for the heat transfer.